biggest opportunity. And we're going to see why. Once we get to analyze some of these buildings, we're going to see why it actually would be kind of easy to do some of this stuff. But where's the rest of the energy going to come from? Well, here's a projection, and I like this one, because we've got all, so here's the future, right? It's projecting the future. So currently producing oil wells are actually going to go down, and that's as predicted. Then you have some that are yet to be developed and yet to be found. I'm putting my money in that basket. That's potentially a constraint. Of course, if it's expensive enough, someone will find a way to get more oil. So tar sands in Canada, for example, if the price of oil goes down, they can't afford to get it out of the ground. But if the price is high enough, it will. So what about renewables? So here's this little yellow bar is the amount of solar that the world is currently using to generate. The amount of solar generation. Here's the amount of hydroelectric generation. Here's the investment over the different years in the different technologies. Put a lot of money into solar for a while. It's not really giving you that much. So it's a big part. Someone over on this end said PV is a pretty cool thing. I mean, someone said it. And it is. But by itself, it's not going to do a whole lot. How about carbon capture and storage? Anyone familiar with that? Basically, you scrub the carbon dioxide out of the smokestack and you put it somewhere. So here's the amount that we have operating. Here's the amount under construction. That's pretty good. Here's some that people are kind of planning about. And here's where they're really thinking hard about it. Well, all of that adds up to about 1% of global power sector emissions. So it's something. But if we don't take the pie down, your percentage of the pie is still going to be pretty small, right? Here's a normal projection by area of the globe. Here it is by energy consumption. So housing, we've said buildings are important. I think this is a pretty good place to be working on this problem, right? We've got big opportunities. And we've seen where fuel shifts actually work, right? So here's our carbon dioxide emissions. Can anyone spot why the carbon dioxide emissions went down for 2009? Anyone know what happened in 2008, 2009 that might drive carbon dioxide emissions down?
The financial crisis?
Yeah, economic activity ground to a halt. So we're not doing anything, so we're not emitting much carbon dioxide. Then it goes up, but not as far. And then it starts to decline. Can anyone see here, just with what's on the graph, what would be responsible for that decline? What's the thing that we see increasing while this is decreasing? This is oil, coal, natural gas. I don't know if you can see it. This is fuel consumption in the United States, different fuels. We're using more natural gas. Well, natural gas has 4 hydrogens for every 1 carbon. So you can get a lot of energy without a whole lot of carbon emissions, compared to, say, coal, which I think has 18 carbons. So it's a dirtier fuel. So as we reduce our coal use, because natural gas got cheap because of hydraulic fracturing, which will be a subject of discussion, we actually did reduce our emissions. So that's not cool. Okay, this is not where I'm supposed to stop. What's that?
3:45.
Oh, 3:45. Oh, in that case, I'm awesome. I mean, not awesome. I'm not awesome. I'm doing well. So here's us again. This is a little bit out of date, roughly. So about 19% of the world's energy consumption is us. We have about 5% of the world's population. About 40% of that is in buildings, of which residential is a slightly bigger part. And you can see here that it's mostly natural gas, nuclear power. Most of us don't have a nuclear power plant in our house. So that's electricity. Not a whole lot of petroleum, and a reasonable amount of renewables in that pie. Let's look at the pie in a kind of an average U.S. house. So what's the big Megillah? So heating, space heating would be a big thing. What about, and then space cooling, right? That would be good, and then water heating. So those are the things you really want to think about. So that's kind of a rough picture of where we use energy in houses. This is a slightly different picture. It's actually a pretty kind of optimistic picture. But so here you've got $1,900 per year, and you can see 49% of it's in heating and cooling, 13% in water heating, 10% in lighting. No, wait a minute, go back here. This was 45 plus 9. That's more than 49%, right? And then the water heater is 13% here, but it's 18% there. Can anyone figure out why these numbers are different? Apples to apples? What's the difference here? Units here are energy use, in fact, BTUs. Units here are dollars. Different fuels cost different things. So your budget, your energy budget may not be the same as your money budget that's going into energy. That makes sense. So this is kind of a different way of thinking. This is the household's financial flows, which are slightly different than its energy flows. And so all of that is an input into our mechanical systems, right? So heating and cooling, water heating, lighting, electronics, clothes washer and dryer, refrigerator, dishwasher, other, which is basically electronics. All of that's going into this one part of the system. But this input into the system is operating in an entire building system. And so if we want to change the size of this, we have to use these other things as well as mechanical systems to change the amount that's going in. Right? So that's the thing, that's where we have our leverage. Now I've talked about a house, the system as a house. I showed you that same graphic before. Of course, that's not necessarily where we want to draw the boundary. Should that be not just inside the house and its immediate environment? Should it be its entire neighborhood? Should it be the grid that it's attached to? Should it be a municipality? The boundary you set to your system can make a big difference on what decisions you make about what's the best choice for whatever your goal is. And then that's going to impact what fuel choices you use, all those sorts of things. What about transportation? That's something that's usually left out of the house system, but can make a big difference. If I built a beautiful house out in the east, I can't seem to think of a non-smart way to say backwoods place. Somewhere in the backwoods, and I have to drive a long distance. Is that really an energy efficient house? Yeah, everyone likes to reuse, right? This is called the Sankey diagram. And what it does is it shows stocks and flows. And so we can see we can see how different sources go through different parts of the economy. And I'm actually going to ask you to play with this on your own. So there's an interactive thing. Let's hope this pops. All right, so this is something that I'd love to have you play with on your own because it's pretty interactive. So you can see, now everything is in quads. Does anyone know what a quad is? It's quadrillion BTUs, quadrillion British thermal units. We are going to talk about this energy unit. For this point though, all you need to know is it's the unit we're using, it refers to energy, and it's all the same whether it comes from nuclear, hydro, coal, wind, geothermal, natural gas, solar, not very big, petroleum. So you can see the relative size right? So just, this is kind of a visual thing for you to just see the relative size, and you can see where it goes. So I just want to briefly talk about transportation. Actually, yeah, so if you look at transportation, that's where the oil goes, right? So the oil is going, most of it's going to transportation. But here's a neat thing. When you go over here, you can see the amount that goes to waste, so lost energy, from the whole energy system. You can see that more than half of the energy is just wasted. That's just lost. And here's the amount that provides energy services. Okay, so less than half of our inputs comes out as the thing we want, whatever it is that we wanted from these different economic sectors. Why are you giving me that? And then we can ask ourselves, okay, when we say used energy, are we actually getting what we want from that energy? So let's look at transportation, for example. We put in a bunch of fuel, get this tiny little, about 20% that comes out as actually providing transportation. But let's say you put two of us in a car, and we want to go from here to Boston. What percentage of this actual, the energy service, so forget all the waste, just what percentage of that is actually moving us to Boston? Just rough guess. Anyone got a guess? About 10%, right? Because we got the wheels, we got rolling resistance, we've got the aerodynamics of an average car, we have the weight of the car. You got like 2 tons of car moving around, not very many pounds of person, right? So when we think about transportation, which is not what we're going to be thinking about very much, but it's kind of, we've all been in cars, right? So it kind of makes sense. So public transportation may be a solution rather than more and more better cars. Or maybe we need to get a much more efficient way of taking energy and putting it into cars so that we get the same amount of energy service, but maybe only a tenth of our energy input is wasted as heat. And we can kind of think about ways that you could do that. It's possible. And then if you look at power plants, we put in nuclear power, coal, plenty of coal, natural gas. We put all these things into power plants, right? And you can see. So everything that goes into power plants, the vast majority of it leaves as waste. Okay, so about 67% of the input is lost. The rest of it is going to various things, right? So we have some going to the residential sector. Again, here we're saying, look how efficient the energy input to housing is, right? It says here we put in a certain amount from electricity, and we're getting out, say, 80% in energy services. Well, are we actually getting those services, or how much waste is in the service that we're getting? So we're not actually getting a service. So for instance, a television that's on and nobody's home, what service is being provided? I mean, unless you've got a cat who likes to watch TV, probably none. So this is something I'd love to have a chance to explore. But with electricity in particular, right, so with electricity in particular, we have this huge amount of waste. So there's a chain as we transform energy from one form to another. It comes in as coal, it gets burned and turned into steam and pressure, which turns a turbine into mechanical energy. And there's loss at each one of these stages as you transform energy from one to the other. And then it gets transmitted as electrons down a power line, and there's about 10% attenuation loss, so you have a lot of just loss in the power line. And even if you're 100% efficient at using the electricity in the house, you've got this burden of 3 times that amount of energy just in waste when you use electricity. So using electricity carefully is kind of important. So here's this kind of 62% efficient natural gas water heater that's still provides the same amount of energy input